Hello, my name is Eunpil Kim. So today I want to present about the free convection characteristics in a channel flow with a vertical plane fins. This is the schematics of a heat pipe system. This is LED system, so heat is generated by this system. So the heating is very problematic in electronic device. So in this case, we want to remove heat from this side because of LEDs depends on the temperature. It is involved with the durability and the sustainability. So to remove this one, we have two very vertical sections. The first one is the evaporating section, and the next one is condensing section. So to remove heat, probably we put a kind of a vertical plane pins along this pipe. So this is our suggested model. So this is two horizontal pipe. Across that pipe, we put vertical plane pin like this picture. Next one is the schematic representation of a detailed geometry. So the first one is the perspective view. There are two tubes like this one. Between the center over two tubes, we call it P. So the plate is this is width, this is height. So we just focused on two vertical planes because we wanna know the variation of parameters W, H, and D, as this one is a side view. Let's see. This is the computational domain over our geometry. You see in here, we separated this computational domain from the whole domain because of we compute the whole domain. It takes so long time, so we just separated this system from the whole system. So we focused on this one in detail, so we can, after that, we can know the parametric study. We can review the parametric study to get the optimized design systems. Okay, this is the computational domain. This is a grid system. As you see in this picture, around the cylinder, we have very condensed computational grid. So far from away from this pipe system, we had the coarse grid system. This is our governing equation. The first one is continuity equation. The next one is a momentum equation, and third one is energy equation. This is a non-dimensional system. In here, non-dimensional parameters are Prandtl number and the Rayleigh number. Also, as you see in this system, for the particle plate, to compare our system is right or wrong, we used a kind of standard models of Churchill and Morgan's correlations. In this case, Nusselt number is a function of Rayleigh number and the Prandtl number. This one is suggested by Churchill, and the next one is Morgan's correlation model. This is Rayleigh number and Nusselt number. So for the Nusselt number, we need this one to get the or to calculate the rate of heat transfer, because on this right hand side you have H, heat transfer coefficient, and diameter D, and the thermal conductivity K. So from the Newton's law of cooling, we need H. Next one, the mesh gradient independence result for plane heat vertical walls for this Rayleigh number. So with variation over cells like this one, up to this one, there is a big variation compared to this one. So along this one, there is no big variations. So after that, we can sure the temperature the result is not very the result is very stable. Okay, let's see comparison and the experimental and the numerical Nusselt numbers with the varying Rayleigh numbers. As you see, along this axis you have a variation of Rayleigh number. We compared it with the correlations suggested by Morgan and Churchill, and this one is our presented studies results. So as you see in this figure, the result is very good agreement with the correlation equations. The next one, okay, let's see the Nusselt numbers with the 3 different plate ratio with varying the Rayleigh number. This one is with from 0.8 to 1.4. You see, with increasing the Rayleigh number, the Nusselt number is increased rapidly at the first time. So after this point, the increase is slowed down. And the next one is the temperature contour under the effect of varying plate ratio. So you see this solid line shows the width and the height. As you see in this figure, this profile is different. For the low Rayleigh number, in this case 10 to the third, you have a very vivid temperature variation like this one, because in this case the natural convection effect is very low compared to this one and this one. In this case you can see everywhere, even if the around the tubes we have green colors. So this means in this case the natural convection effect is very high, so that means fluid velocity is high. So in this case you cannot see this kind of very high temperature, so heat transfer occurs very well in this case. And the next one, temperature contour under the effect of varying plate ratio. In this case you see Rayleigh number from 10 to the third to 10 to the sixth. Also we have the similar patterns, but in this case you see along the flow direction you can have high temperature like this one. However, in this case the temperature in this one is just the flow this direction, so this height is very low. In this case is more effective than this one. Okay, based on previous results, we calculate the heat transfer rate. So case A, B, and C, as you see, C, we have a more high heat transfer rate like this one I mentioned about previously. And the next one is the temperature contour of the effect with the varying plate pitches. As you see, A, B, C, the pitches in this case 20 millimeter between two plates, and the next one is 10 millimeter, and third is 5 millimeter. So in this case, as you see in this figure, the pitch is so small, so the flow temperature is very high when you have very small pitches. However, in this case, for the 20 millimeter pitch size, you have very good temperature profiles. So based on this one, as you see in this figure, we change the pitches from 20 millimeter to 2.5 millimeters. So in this case, you see you have a high heat transfer rate like 1.1 watt. So this means for the same size or same geometry, if you have a small pitches, you can put more flat pins because you have small pitches. So you have high heat transfer rate like this one. Okay, let's see. Again, this is our geometry. Okay, let's see. Heat transfer rate with varying the temperature distance. Temperature difference. Temperature difference is this one is a surface temperature to ambient temperature. So in this case, we changed from 30 degrees Celsius to 70 degrees Celsius. As you see in here, the S is changed from 1 millimeter to 4 millimeter. So this one is okay. At the first part of this figure, you have very big slope or big changes. However, in this case, the change is slow and slow like this one. And the next one is in this case, the temperature difference is 30 degrees Celsius, and this one is temperature difference is 70 degrees Celsius. So in this case, you can see more high temperature profile along the flow direction. The next one, heat transfer rate with varying vertical plane pin size. So we change the H values like this one. But in this case, as you can see in here, the temperature effect or heat transfer rate effect is not so big. And this one is a change of width. So we change the 36 millimeter to 48 millimeter. You see, at this point, the heat transfer rate difference is so small. However, when you have the bigger temperature difference, the result is like this one. Okay, we change the S size. In this case, is 30 millimeter, and this one is 1 millimeter. So we wanna see the effect of change of S. Okay, let's see. We change the S 1 millimeter to 4 millimeter. You see, at the first time, the change or the slope is small. However, like this one, you have a big slope compared to the previous one. And the conclusion, when the Rayleigh number is larger than 10 to the 4th, the plate fin geometry effect is large, especially when W changes from 1.0 to 0.8. The change in the heat dissipation is very effective. When the geometry ratio with the same heat transfer area varies, the heat dissipation rate increases as the horizontal length increases. When the pitch is smaller, the total heat transfer rate decreased. However, on the total volume basis, the total heat transfer rate increases. Thus, The smaller pitches are recommended with considering geometric constriction. Thank you for listening. That's all for today's presentation. Thank you.